All right, so next let's talk about, we're out camping and the temperature's low. So if you're out camping, the temperature's low, let's go grab some firewood, right? And we'll put some rocks around so that we protect our combustion from not getting out of hand. We want to move the dirt and stuff away. I think it was just dirt so that we have a controlled space. But I have some logs, right? Which is my fuel. And then I already have oxygen, which is in the air around us, just naturally there. And I add a spark going, and I'll end up with fire. Kind of nice, right? Sit next to it, you feel the heat coming out. That's radiant heat. As you're there, you feel the radiant heat coming out to that fire. It's like, oh, this is quite nice. It's good, right? You ever been camping? Been camping when it was less heated outside? Yeah, is the fire nice? Absolutely, right?
It's a must.
It's a must. Absolutely. So let's talk about a way that, let's say we move into the city and we don't have a house and it's very, very less heated outside and you want to keep it warm. You can't have a fire going in a pavement, right? You can't just pavement on fire. What if we modified that and we put that inside of a barrel? Fuel, paper, whatever we got. Oxygen's already there. A little bit of a fire, right? What can we do to make that burn better? Let's put a little hole in the side here so we get more oxygen in there. They have a nice little fire going, right? You guys ever seen that? Yep. They got a fire going in a trash can?
Movies, TV shows.
What's going to happen, though, is as we're having this combustion, we're going to have incomplete combustion. We're going to have carbon, we're going to have soot, we're going to have carbon monoxide, all this other stuff. But what's great, though, is as that fire is heating that up, all those other gases become less dense. They become less dense. And when something gets less dense, what does it become? Lighter, yes. Becomes less dense, it becomes lighter. So that objects and smoke and gases become less dense, becomes lighter, and it travels up because the cooler, more dense air is pushing down. So it's pushing it up by convection, natural convection. Cool, huh? Mm-hmm. Natural convection. How great is that? Sound good? Mm-hmm. What's great about this is it contains the fire. You can actually feel the heat next to it, right? Without having that bright light there in your face. Smoke's going up. It's great, isn't it? But then imagine that we find a vacant house, and we're going to move into that vacant house. The problem is we have this fire in here, and all that smoke's going to fill up the house. So what if we went and put a lid on this? What happened if I put a lid on this?
No more fire.
No more fire. So I have to put a lid on it, and then I'd have to put maybe a pipe going out through the roof. Did that work? So now I have my fire going. What's happening to all those fumes? It's going outside. How's it going up and outside? Natural convection. That's right. Pretty neat, huh? Mm-hmm. Now basically what we have is what we call a wood-burning stove. The fire is on the inside. The air that you're around is where?
Inside.
On the outside of this metal. The fire's on the inside of this. The air you're touching is on the outside of it. Do you actually touch the fire? No. What's happening is the fire is heating up this metal. The metal is then heating up the air because the air is touching the metal, so that's conduction. But then as the air that touches this metal gets warmer, what does it do?
It's lighter.
Gets lighter, less dense. Then we have convection. So that heat warms up and it rises. The warmer air rises up. And then the cooler air that's less dense comes in its place. So we have this cycle going. And we're actually heating. This is a type of fireplace. We call them wood-burning stoves. We have a little door. We open the door, throw some wood in, close the door. We can adjust how much air comes in. We have the chimney that's going out. And the fire heats the metal, and the metal exchanges that heat to the air. But it keeps the fire and the air separate. But it does exchange the heat between the two. It's what we call a heat exchanger. So far, so good? Mm-hmm. the heat exchanger. Pretty neat, huh? Sounds good, right?
Yeah.
So what we do is we come along and we throw some fire in, get it going, and then what's the problem with that though? One problem is where are we going to put that? Right? Where are we going to locate that? So what we can do is we can take that, we can put it over here in the corner to where it's out of the way. But the problem with putting it in a corner where it's out of the way is what?
It's only going to be heated.
That's right. It's going to take a while for that convection to travel over here to the other side of the room. It's going to be a big issue, right? Mm-hmm. So what we can do to solve that? Anybody know? How about a fan? How about some forced convection? You guys ever had a wood-burning stove? A place where you had a wood-burning stove? So you use it in the corner, right? What if we put a fan behind it? We put it in the corner, put a fan behind it. Now we're blowing that warmer air, forced convection, to the rest of the room. And that air is circulating back around. Does that not make it work better?
Yes.
Absolutely. Yes, it does. Yes, sir.
My grandfather actually had one of those, but instead of behind it, he actually had a heat-activated one on top of it. So it continued to blow, but it didn't require electricity. It just used the heat off the fireplace. It's pretty cool.
That is cool. They make those, yep. So this is pretty neat. So here's what we do. When it gets cool, we open it up, we throw some more logs in, close it. What happens when the fire burns out? That's right, but before you start another one, the fire burns out. We're just blowing cool air, right? The air just feels cooler. We don't want it to feel cooler in the winter, do we? So what we need to do, and then we start another fire up. Does that fireplace immediately get hot? No, it takes a while. So I have to get the fire going and then come back 30 minutes later and turn the fan back on. And when the fire goes out, I got to make sure I unplug the fan and then start the fire again. It's a lot of work, right? I agree. Too much work. So what if I took one of the plug wires for this fan and I put a little sensor right here? So now the plug outlet, I take one of the wires and go in here, from there into the motor, from the motor back home. So now, when I put the firewood in and get the fire going, the fan doesn't come on right away. Once the fireplace gets hot enough, this switch closes, and then the fan comes on. How's that sound?
Good.
It is. And then if the fire went out on its own and forgot to put more firewood in, once the metal cools off, what happens to the fan?
Turns off.
Shuts off. How great is that?
Nice.
The fan comes on and off automatically. Isn't that awesome?
Mm-hmm.
It's a fan control. Fan switch. But it's kind of a pain. What's the hardest part about having heating your house with wood burning stove?
Adding the wood.
Adding the wood. That's absolutely right. We got to go out, not just adding the wood, but chopping the wood. You got to go out and cut it, load it up in the truck. You got to take it back. You got to stack it at the house. You got to worry about all the bugs coming out of it. You got to bring it inside. You got to keep it dry. Make it small enough to where it'll actually fit into the wood burning stove, and then keep it going. It's great fun.
When you have nothing else to do.
It's never fun. Even if you have nothing else to do, it's still not fun for me. So let's replace this fuel with a different type of fuel. So let's replace this fuel with natural gas. But the problem is, if I have natural gas, and I bring that pipe in here, this is giant uncontrolled flame. Imagine a 3/4 inch pipe or 1/2 inch pipe, which is an uncontrolled flame coming out at the end of it. Kind of dangerous, right? Kind of like not what we want to have. So we have to do some things to make this work. For one, I'm going to have to put a shutoff valve here. And we call this a gas stop. Called a gas stop. Some people call it a gas shutoff valve. Some people call it a gas stop. I have one right here in my bucket of goodies. Gas stop. This is the gas stop. If I turn it where it's going inline, you can see right through it. If I turn it where it's sideways, can't see through it anymore. It's a gas stop. It's also known as a gas shutoff valve. Plumbers have other names for it. As plumbers, you go to a plumbing supply house, there's one name only that they know it by, and it's the proper, legitimate name. However, I'm not going to use this name in front of my customer because it's going to offend them. Jason, what is this part also called?
Gas cock.
A gas cock. That's what it's called. Now, when I go to supply house and I say, yeah, I need a gas cock, right? They know exactly what you mean. But I don't go to Mrs. Jones and say, Mrs. Jones, you need a new gas cock. Because she's probably going to slap me and be mad and kick me out of her house, right?
Yeah.
So even though the plumbing professional name for this is a gas cock, I don't use that when I'm talking to my customer. I call it a gas stop or a gas shutoff valve. That's what we're going to put here to control the gas. We can turn it on and off and on and off and on and off. The other problem that we have with this, though, pass this to you. You can pass it around. The other problem we have with this is it's just too uncontrolled over here. So what we need to do is have a pressure regulator. A pressure regulator is going to regulate the pressure, but in simplicity, it's going to reduce the pressure. It's going to drop the pressure down. So it's going to drop it down to a controllable amount. The other thing I'm going to do is on the very end of this pipe, that pipe is just too giant, it's too big. I need to have a smaller amount coming out. So what I'm going to do is thread a fitting on the end of that. And that fitting I'm going to thread on the end of it is called a spud. It's called a spud. Like a potato, spud. This is a spud. Inside of the spud, what we have is a hole drilled in it. That hole that's drilled in the spud is called an orifice. It's an orifice. So this is a spud with a hole drilled in it. What's the name of that hole that's drilled in it? An orifice. So now that I have reduced my pressure and I have this spud on there that I can change this out and an orifice on there, I can control how much gas comes out. Pass it to you. Take a look at it. But then I'm just shooting this flame out at one angle. So what we're going to do is we're going to add to this also a burner. A burner. What a burner is going to do is it's going to, one, mix the air and the fuel together. So we're going to bring a burner through here and we're going to allow it to where it mixes the air and the fuel. So notice how I'm shooting the gas in. I also have gaps in the side. If I shoot gas in through the middle, it's going to create a bit of a vortex. And that vortex is going to be pulling air in it from the side. What do I have to have combustion? Oxygen. So what we're having is it's pushing the gas and it's pulling oxygen beside it. The oxygen and the gas mix in the middle. And then the burner does two things. It mixes the fuel and the oxygen, and it also directs the flame. You may have a gas stove. You have a burner in your gas stove. Guess what your burner does? Mixes the gas and the fuel and directs the flame. That's exactly right. That's what's happening. So it's mixing the gas and fuel and directing the flame. So now look, I have this nice flame going off in there, right? Now I don't have to go chop firewood. I don't have to bring firewood in. I don't got to stack it. I don't got to keep it dry. I don't worry about the bugs. I just come over here, shut this valve off. My flame goes away. When I open this valve's open. I reach in here with the lighter, light it. Once I get it lit, then I got my flame going. After the flame starts getting warm, this switch closes, brings my fan on. Starts heating up the house. Then, I'm like, oh, the house is kind of warm. I go over here to the valve. I shut the valve off. When I shut the valve off, what happens to the flames? Goes out. Is the metal cool off immediately? No. Takes time, right? So the metal's going to be warm. This switch is going to keep the fan on to cool the metal off. Eventually that metal's going to cool off. What's going to happen to this fan? Shuts off. That's a perfect thing, right? Isn't it great? So that's what's happening. And then, it feels kind of cool. So in the middle of the night, you wake up, you come over there, you open the door, you reach in, you light it with the lighter when you turn this valve on. Sound good, right? The problem is having to open this door, reach in there, and light that flame. Kind of not a fun thing. So what we're going to do is have maybe a little bitty miniature flame that will direct or guide or pilot the main flame. So what we're going to use is a pilot light. So here I'm going to make a little bitty pipe that comes over here and connects right here, because on the back side of the regulator, where there's a little flame burning. But if I turn this valve off, what happens over here? Shut off my pilot light. So I'm going to need to add another valve. I'm going to put another valve here. And I'm going to leave this valve on all the time. So here, my pilot light is getting its gas before my main valve, right? Kind of neat, huh? Yeah. So if I have my pilot burning, a little flame all the time, and it gets cool in the house, all I got to do is reach in here, turn this valve on, gas flows through the manifold, through the spud, mixing with primary air, across that pilot light and burns into a flame. Once the heat exchanger heats up, the switch brings the fan on, the fan comes on. It's kind of nice, right? Yeah. Then once I get warm, I shut this valve off. What happens to my main flame? What happens to my pilot light? Stays on. It's exactly right. Sounds good, doesn't it? Isn't that great? Isn't that nice? Yes. Isn't it wonderful? It is wonderful. All right, but what happens if, say, the wind blows back through this pipe and it blows my pilot light out? Gas is going to be leaking and filling up. And I didn't know, and I turned this valve on, and now I got a bunch of gas filling it all up. Does that sound good? No. You want gas filling that heat exchanger up? No. Yeah, I don't either. So we need some kind of a safety to make sure this doesn't become a bad problem. So what we're going to do is include a component called a thermocouple. A thermocouple is a device that when heated creates current and voltage. Thermocouple is a little device that pilot's going to burn on. It's going to convert heat energy into electrical energy. So as that pilot light burns against this thermocouple, it creates heat energy. That heat energy creates an electromagnetic field that keeps this valve open right here before it. So we have a little solenoid valve right here. So if the pilot light goes out, are we going to create voltage and current? Is there going to be anything to energize the electromagnet? So if the electromagnet goes out, what's going to happen to this next little valve right here? It's going to close. Now if this valve closes and I open this valve, is any gas going to flow? No. Is the pilot light going to let gas flow? No. But now I need to relight it, correct? So if I go to relight it, wait, with this valve open or closed, I can't get any gas coming out. So I need a way of bypassing this. So what we're going to do is we're going to push a button on the opposite side of here. So we're going to paint it red. So now when I push this button, it manually opens that valve. It holds that solenoid valve open. So I'm going to hold that button open, which is going to allow gas to flow through this little bitty pilot valve. Follow me? Mm-hmm. Then I'm going to reach in and light the pilot light. Now there's going to be a little flame burning against that thermocouple. Are we going to be creating voltage and current? That voltage and current will take about 30 seconds to a minute, and it's going to finally create an electromagnetic field, and it's going to keep that valve open. So I don't have to hold the button anymore. And the pilot light will stay on. How cool is that? You guys ever lit your water heater before? That's why. You're going to have that little button so that you can override that little solenoid valve to let gas flow. When gas flows, we can then light the pilot light. And we have to hold that button so it creates enough heat energy to create enough electricity to keep that solenoid valve open. Neat, huh? Isn't it cool? Okay. So now when I open this valve, gas flows through here, across the light, ignites into a flame. Life is good. So now all I got to do, middle of the night, it gets cool. I just run downstairs. I open this valve. Gas flows in here, across the pilot, burns into a flame. Go back to bed. As soon as that heat exchanger heats up, This switch closes, brings on the fan, starts moving air into the house. Then, wake up in the middle of the night, a few hours later, it's hot in the house, run back downstairs, I close this valve off, the pilot stays on. What happens to my main flame? Goes out. Is this fan going to shut off immediately? No, it's going to stay on a little bit until it cools off this heat exchanger. Pretty neat, huh? You got a fully automated system. All you got to do is wake up every hour or so, run downstairs, and open and close that valve. Isn't that cool?
Not that part.
Oh, well, you want to automate it more? Is that what you're saying?
Well, why not? Rather than wake up every hour.
Okay, well, let's see if we can come up with a way to automate this more. So, what if I replace this valve with another solenoid valve, kind of like this one? So I put a solenoid here. So now that's an electrically operated valve. I create an electromagnet and it opens the valve. I kill the electromagnet and the valve closes. How does that sound? Sound good? A solenoid valve. Then, I need something to control it. So let's put a transformer over here. So over here we're going to have primary and secondary. Primary plugs into the wall outlet. Secondary, we're going to have the letters R coming out of it. What if we hook that R wire to our thermostat? So we have the R wire from the transformer to the thermostat. So that when the thermostat had a call for heat, it would connect it to the W wire. Where do you think we'd run that W wire? To the solenoid valve. And after we do work in the solenoid valve, where should we go? Home, 24 volt coming to the transformer. So let's see if this would work. All right, so the temperature during the day or during the night cools down. Thermostat calls for heat, connects R and W. We energize my electromagnetic coil. That opens the valve. Gas flows through the manifold to the spud and orifice, mixed with primary air in the burner, across the pilot light, igniting into a flame that burns inside the heat exchanger. The heat exchanger is going to heat up. It doesn't heat up right away, but it's going to take a little bit. It's going to heat up. Once the heat exchanger heats up, this switch is going to close, send power to my fan motor. My fan's going to move air through it, and I want to heat the house. When the house heats up, the thermostat satisfies, breaks R&W, kills my electromagnet. Spring causes that to close, shuts off the main gas, but the pilot light stays on. Awesome, right? Fully automated gas heated stove. But then, what if the wind blows this pilot light out? What's going to happen?
Get out of bed and go back.
The thermocouple is no longer going to create current and voltage, which means my solenoid valve over here is going to close. Now the thermostat calls for heat, and this valve opens. Is there going to be any gas flowing? No, because it had to go through this one first. Pretty neat, huh? But what if so I have to come back through, I press the button, I relight that little pilot valve. So I get my pilot valve lit. So I got my little flame burning. Right? I hold this, it stays open. I call for heating. This comes on, heats up, everything's running good, right? But what if something happened and this got too hot? What if I had a safety on here to prevent this from getting too hot? Maybe I would put a sensor right here that's normally closed and it opens on temperature rise. And this W wire, I break it. So if it gets too hot, it would shut off the combination gas valve. I'm sorry, the solenoid valve. Isn't that cool? Mm-hmm. And I still have my main gas stop over here, so if I need to work on anything, I can shut it off manually. But I got my automated controls here that turn on and off as I need. Isn't that cool? You think that's neat? You like it? It's great. The thermostat just closes the switch. My solenoid valve does the work. The safety is that pilot light and the thermocouple on it. I've worked in houses that were designed before thermocouples came out. And the pilot would blow out, and it would just keep dumping gas. And I would tell them, Mr. Jones, you have a system here that's very old and has zero safety controls. And if this pilot ever blows out, there's nothing to stop it from filling your house full of gas, waiting for you to come home and flip a switch to explode. Nope, I've had it like that for all these years. I do not want to change it. Yes, sir. Write on an invoice. System has a very dangerous old furnace. out of date, no safety controls, not even a pilot light. This is a big issue. Customer did not want to do anything about it. Boom, you're done. So now when Mr. Jones dies in a fire, well, I told you so.
This family comes looking to sue.
They're going to look for sue somebody.
Oh, yeah.
And you have an invoice noted very clearly, you're going to be okay. Pretty neat, right? This is an automated gas stove. Let's turn it into a gas furnace. What we're going to do is put all of these controls here in a box. I'm going to move this fan to be a blower. I'm going to put all of this here into a big box. And I'm going to move this power wire here. So where the same power wire powers it. I know the drawing's sloppy and messy, but when we get out to the lab, it'll make more sense. So now I'm blowing air on the outside of that heat exchanger. Where's the fire burning? Inside. Does the fire and the air ever mix? No, it's completely separate. The air we're burning is separate from the air going around it. Pretty neat, huh? Mm-hmm. Yeah. Now we have a gas furnace. We have now made a basic gas furnace. But let's modify it a little bit more, because now we've caught up to about 1992. Instead of having one big giant drum, what if I had smaller drums? And I had the fire burning in individual little drums. And instead of having one orifice, I had a manifold that gas flow through, and I'd had, say, 3 spuds with 3 different orifices that had gas burning in 3 different chambers. Would there now be more heat and more fire touching more metal? Yes. Would that be more metal touching more of the inside of that fire? Yes. Now on the outside of it, would there now be more hot metal touching more air, cooler air? Would that not increase surface area? Yes. Would it not speed up the second law of thermodynamics? Would it not make it more efficient? Yes, sure. That's what we do now. But wait, there's more. If I wanted to heat that even more and make that even more efficient, I could take and put a little fan motor right here and actually pull a draft through this heat exchanger. But then if I do that, I could actually make my fire burn sideways. If I pulled a draft through here and had my flame burning sideways, it would actually pull it through the tube. And the flame's only going to burn in this first section of tube right here. The hot gases are still going to go back and forth, and this flame is pulling, this motor here is pulling it through. Isn't that neat? Mm-hmm. So what we call that is an induced draft motor. We have one right here. This is an induced draft motor, where we're going to have multiple heat exchangers come together. This motor is going to pull that draft through it, and our chimney, which we're now going to call a flue pipe, is going to connect here. And we're going to pull a draft through it and force it out. And this is a metal blade. And it's the inducer motor, or a combustion blower, they call it sometimes. It's going to force a draft through that heat exchanger. Now let's talk about the heat exchanger.
Flue pipe?
Flue pipe. Like you have the flue, or I just flew in, but it's spelled different. You want me to spell it for you? IT. Come on, that was funny. This is the heat exchanger. This is just one tube. I can actually blow the fire inside the tube. There's a chamber here. The fire's burning inside, and the air is blowing on the outside. The fire's only burning in this first chamber, but the gases from that fire are still hot. So the gases pull back and forth and back and forth. And then notice how we squeeze the pipes towards the end. Well, by squeezing the pipe, I have more gas touching more metal. I get better heat transfer. This is one style of heat exchanger. The fire burns on the inside of that pipe, and on the outside of that pipe is the air. Here's another style. On this style, we have the fire burning in this first tube. Then it's just the hot gases pulling. But notice they took this tube and made it smaller, and they put these little divots in there so they can increase heat transfer. It's another style of heat exchanger. I could have 3 or 4 or 2 or 1 of these. To make the fire burn at an angle, we need a special type of burner. We need a burner like this. We call it a jet burner or an in-shot burner. The spud fits here. It mixes the air, comes in the side, and shoots it across, and then the inducer draft pulls it the rest of the way through. These are the burners we're going to be using. Then, what we started doing also is we took all these components, the gas shutoff, the pressure regulator, the pilot valve, and the solenoid valve, and we put them into one component. Is this component a combination of multiple parts? Mm-hmm. It is. So guess what we call this? A combination gas valve. Because it's a combination of a pressure regulator, a solenoid valve, and some other stuff. So here we have the pilot, so we have to actually push it down for the pilot to work. We have 2 wires for our solenoid valve. We have an adjustment for a pressure regulator. We have a port over here for our pilot tube. And our gas in and gas out. But then let's add technology. That flame burning all the time used a lot of gas. You don't sit there and use up all that gas, do you? No. So they said, instead of having this pilot burn all the time, let's come up with a system that we can light the pilot first. So here we have that system. So these are some of the older style burners. Before they had the in-shots, we had the big shells that they fit in. This is our manifold with our spuds and orifice. This is our combination gas valve. Here's our pilot tube, our pilot lights. But then we had an electronic ignition, like a spark plug. We had a spark igniter. We had a step-up transfer that stepped the voltage up to 10,000 volts. With 10,000 volts of pressure, you can make voltage jump through the air. Electrons jump through the air, which is called a spark. So we started using a spark igniter. We had a spark, and we ignited the pilot light. And then the pilot light lit the main burners. Combination gas valve. This is the manifold, spud, orifice, burners, pilot lights, electronic spark ignition. But then they said, hey, instead of having a spark igniter light the pilot first, what if we used a spark igniter to light the main burner? They started calling that DSI. It's called direct spark ignition.
Does that eliminate the pilot?
Yes, eliminated the pilot immediately. We just said, if we can, instead of lighting the pilot light and then the pilot light lighting the main burners, how about use a spark to light the main burners? So they started doing that. The problem, though, is how do we prove a flame? What kind of safety do we have? How do we know that that flame is still working?
Safety switch.
What we need is a sensor for it. So we're going to need a flame sensor. I'm just writing these words because we're going to come back through these words and go through their components a little bit later. And then, what if this motor right here stopped working?
You won't get any heat.
Well, if that motor stopped working and I sent gas and fuel at an angle, but there's nothing pulling it through, there'd be a fire rolling out, wouldn't there? So what happens is, we're going to need some kind of a safety, which is going to be a vacuum pressure switch. And we're also going to need a rollout switch. So if the flame rolled out, we could shut stuff off for protection. Now we've covered a lot of components, but I had to quickly get you from the first initial heating styles all the way through pilot lights, which they stopped making pilot lights in 1992. So if you have a customer that has a unit with a pilot light, you need to sell them a new system because it's going to be old, outdated, no safety components, and probably on the verge of leaking carbon dioxide anyways. So if you have a customer with a pilot light, I would just say, hey, you need to get a new unit. Don't even worry about the other steps because it's going to be dangerous. And then say, hey, look, I don't feel comfortable working in this because your life's at stake and I want to read about you in the news. So that's why I don't teach the pilot lights anymore. I used to love to teach. I could go on for days teaching out just pilot lights, all the different types and all the combination gas valves. But it's not relevant anymore because if you have a customer with a pilot light, they'd need a new system. They don't last forever. What's 2018 minus 1992? What? 26 years old. After 20 years, that heat exchanger is going to be shot. Need to replace it. So the two types of pilots that ignitions we have is direct spark ignition, and hot surface igniter. Those would be the two that we're going to focus on. We're going to focus on, instead of thermocouples, flame sensors. What we're going to do before we get into all this other stuff, we've covered a lot of components. I want you guys to take your notebooks. I'm going to go out to the lab, look at those furnaces. Look at these gas furnaces and start thinking about all the stuff we talked about. See if you can identify, just simply identify some of the parts we've talked about. See if you can look at that furnace and see how it's working. Right? Once we come back in, we're going to talk about the modern furnace components, and then we're going to put them together in a sequence of operation, and then we're going to go back to the lab and we're going to run through the sequence of operation. Sound good? Mm-hmm. All right, so let's go to the lab.